Here we have three integrals to evaluate using u-substitution. The first one is the integral of e to the 3x plus 1 dx. So remember, what we're looking for when we do u-substitution is some kind of u such that the integral can be written as oftentimes f of u, u prime. Okay, so not always the case, but in general, the first thing to kind of look for is a setup like this. Can we find such a u? In our example, integral e to the 3x plus 1. Well, let's start by looking inside the function, inside e to the something. And we can call this, look, 3x plus 1 u. So if u equals 3x plus 1, then du dx must be 3. We can then solve that for dx to get dx equals du over 3. And we sub this dx in to the dx in our integral. Well, this then gives us a new integral. Now we have the integral of e to the u times du over 3. And for the first time, we have something that doesn't cancel out. Right? In the examples we did before, this 3 down here, or whatever constant we have, always canceled out. But now it doesn't. But that's okay. We'll just bring it out to the front as 1/3. So this gives us 1/3 times the integral of e to the u du, but the integral of e to the u is simply e to the u again, so 1/3 e to the u plus c, don't forget your plus c, but now we pay it back. Remember that u is actually 3x plus 1, so we back sub that in to get 1/3 e to the 3x plus 1 plus c. And if there's ever any doubt as to whether this is the correct answer, we can always take the derivative and get the integrand originally inside our integral back again. So there's a built-in check for this if you have any doubt about whether or not your answer is correct. Let's try part B. We have the integral of x cubed times the quantity x to the 4th plus 16 all raised to the 6th dx. Kind of looking for a u nested inside a bigger function that the derivative of the u is outside the function. And it doesn't have to be the perfect derivative of it. It can be off by a constant. In fact, it will often, even almost always, be off by a constant. So we're not looking for the exact derivative, but look what we have here. We have x to the 4th plus 16. That can be our u, and note that's inside this, something function to the 6th. And our du will be of the form x cubed. Yes, we are missing some constants, but those constants will take care of themselves when we do this du dx business. So let's do the du dx business. So we have u equals x to the 4th plus 16. Then du dx is, all right, so the derivative of that, 4x cubed. All right, solving that for dx gives dx equals du over 4x cubed. Okay, let's sub that into our integral, and we sub our u in as well, and see what we get. So this integral becomes the integral of x cubed times u to the 6th, but dx is du over 4x cubed. Well, our x cubes cancel, but note that we still have this 4 hanging out, which I'm going to bring out as a 1/4 to the front of the integral. So this becomes 1/4 times the integral of u to the 6th du. And now we have something we can integrate. Okay, well, using the power rule for integrals, this 1/4 hangs out, and then we get u to the 7th over 7 plus c. And let's back substitute and simplify this down. Remember, u is actually x to the 4th plus 16. Now all that's raised to the 7 over 4 times 7 is 28. And don't forget your plus c. Okay, for part C, we have the integral of x e to the x squared dx. Why don't you pause the video, try that one on your own, and see if you can get that to come out. Okay, well, we're oftentimes looking for a u inside of another function. So we have e to the x squared. So what if we let our x squared be u? So u is x squared. Then our du dx must be 2x, which we can then quickly solve for dx to get dx equals du over 2x. Subbing that in up here into our integral, this gives a new integral of x e to the u times du over 2x. And if you've done this correctly, you should be left with only u's, right? You never want to have mixed variables inside an integral like this. That is until Calc 3, and then you start having all kinds of variables. But for now, we only want one variable inside of each integral. So if you end up with x's and u's in your integral, something's gone wrong. You need to go back to the drawing board. Well, we do have this 2 down here, so that's going to come out to the front as a 1/2. So this gives 1/2 integral e to the u du, but the integral of e to the u is simply e to the u, so this becomes 1/2 e to the u plus c, and recall that u was x squared, so finally we back sub to get 1/2 e to the x squared, that came from right here, plus c.